So my name is Alex Sudoroff, and basically we're teaching computers 101. So now that we can advance to the next slide, let's find out what's there. I had a little introductory section that I'm going to breeze through very quickly because we're kind of short on time. So reverse engineering is the process of taking an application or a process or some kind of network traffic or anything else that you can observe about a computer system and figure out how the computer system works without necessarily having access to its source code, documentation, design, and so on. So it is widely used for various nefarious purposes in the computer underground. People use it to crack copy protections, develop exploits, operating system reversing. It is also used in the security industry pretty heavily. A lot of products like antivirus are based on reverse engineering samples of malware day after day after day. Also, a lot of big security companies have to reverse engineer patches, reverse engineer various attack tools to understand how they work and be able to stop them, and so on. So the goal for this class is to do a very brief introduction to reverse engineering to show you what it looks like. And we're going to take a very simple program written in C, compiled as an executable file on Windows. And we're going to look at that program and figure out what it does and kind of recreate its source code. Not completely, because you can't really do this in like a single hour, but I will show you the steps that you have to take. And if you're interested, you can take this home and you can do a little bit more work and actually get the source code of the program out. So we'll start with a brief introduction to x86 assembly. Now this is crucial because when you don't have the source code to a program, the only thing that you're going to have is the machine instructions. So a x86 CPU, which is what all of these computers have, has its main memory, which is split into the stack and the heap for the data that the application uses, and then the code of the program. The stack is used for local variables in C. The heap is used for anything allocated with the cmalloc and free functions. You have registers. The registers are single elements of the CPU that store values. They're 32-bit long, so they can only store one 32-bit integer in each register. You have the EBP and ESP registers, which usually point to the stack. ESP is the stack pointer. It shows you where the end of the current end of the stack is. So when you add data on the stack, the ESP register kind of moves down, and then when you remove data from the stack, it moves up. EIP is the instruction pointer. It always points to the instruction that is currently being executed. So if you have any jumps, or if you call a function, the instruction pointer is going to move to the instructions of that function. And then you have the general purpose registers, which are listed here. Those registers are just used by the program to store temporary values and operate on them. Then you have some. So what are these operations? You can do arithmetic instructions where you load a constant into one of the registers, and then you can add registers together or you can subtract them. So these instructions here load the value 2 into EAX, 3 into EBX, then add them together. Notice that when you add them together, there's only 2 arguments to the add instruction, EAX and EBX. This is because the first argument serves both as an argument to the addition and also the destination where the result is stored. So this is basically equivalent to a plus equals operator from C. And then at the bottom there you have a sub instruction that just subtracts an integer from the register. This is all good, but if you need to work with more data than you can store in the registers, which is very limited because there's only like 8 registers, you need to store the extra values that you're going to operate on in memory. And to use them, you have a series of instructions for loading and storing data in memory. So you cannot usually operate with the data in the memory directly. You have to load it into the register, then perform the operations on the registers, and then maybe store the result back into the memory. So here you have the instructions for loading the contents from some address in memory, and then storing the contents of a register in that place in memory. Next, we have conditional branches. So if your program has any loops, they're going to be implemented using branches like this. So you have instructions like CMP, which just compares 2 arguments. And then based on the result, you have a set of conditional jump instructions, which perform a jump somewhere else in the program if the two arguments were equal, or if one was greater than the other, or less than the other, or less than or equal, and so on. And finally, you have the jump instruction, which does an unconditional jump. So that's the equivalent of go to in C. Then, if you have a function, you would call it with a call instruction. So here's the call instruction. And then when the function is executed, usually the function will save some of the registers onto the stack. And then when it finishes doing whatever the function does, it would restore those registers. This is so that the code can assume that when a function is called, those registers like ESI are not modified by the function. So you can because the code always shares the same registers. So when you call a function, you don't want that function to mess up the contents of the registers that you had before you call the function. And then finally, at the end of the function executes a return instruction, which reads the return address from the stack and jumps back to it. So that executes a return back to the place where the call instruction was. Okay. So I'm going to go through this section really quickly too, because it's kind of long and it's not that important for understanding the program that we're going to look at later. This is mostly background information, but I want to get you guys into the IDA disassembler as quickly as possible, so we can spend more time there, because that would be easier to understand than just like the dry lecturing slides. So the instructions that you're going to see, the assembly instructions that you're going to see of the program, do not correspond to the C source code directly. This is because the compiler takes the C code and then it performs optimizations on it. And those optimizations have the effect of modifying the form of the code a little bit without modifying its operation. So the code still does the same operations, but it just does them more efficiently. So for example, one of the optimizations is inlining. So here we have some C code that has a function called foo that just adds its 2 arguments, and then we call it. So when the compiler sees this, it has if it's not an optimizing compiler, then it's going to create a separate function, and then it's going to call that function, and then the function will add the 2 arguments and then return. But the calling and returning from the function take precious CPU cycles. So because the body of the function is so simple, the compiler can just put it in the place where the call happened. It can replace that call with just the addition. So it doesn't need to create a separate body of the function. So if this function is called from a few different places, the compiler is just going to copy it in all of those places. Obviously, that expands the size of the code, but for something as simple as this, that's not a problem. It's not important. Not important. This one is kind of important. So in this optimization called common subexpression elimination, that's a compiler theory term. So if you don't really need to care about what the optimizations are called. You just need to be aware of them so that when you see the results in the assembly code of a program, you can kind of imagine what the compiler did to get to that point from the C code. So here we have two variables, A and P, that are both computed using somewhat complicated expression, but the z plus 1 term there is the same in both. So the compiler will notice this, and instead of computing it twice, it will compute z plus 1 the first time. It will store it in a temporary variable. This can be a variable in memory, or it can be a register. And then after this, when it computes A and P, it will use that temporary variable. So, yeah, there's a bug there. This z should be temp. Sorry about that. But you caught it, which means that you understood the optimization. Then sometimes the compiler completely removes part of your code because they're not necessary. For example, here the compiler can very easily detect that the value of b is always going to be 9 because it's based on the same operations. Nothing is going to change at runtime. So it can just replace all of these calculations with a call to func with the argument 9. Sometimes you're going to have entire chunks of code that are missing because the compiler proved that they can never be executed. So here, for example, we have a check if a is less than 0, but right above it, we assigned 1 to a. So the compiler will see that a is always 1, so this code can never be executed, and the compiler will not output this code in the program at all because it's not necessary. Another thing that you're going to see very often is how the compiler replaces some calculations with more efficient forms of the same calculations. For example, instead of multiplying a value by 15, the compiler is going to shift that value by 4 and then subtract the same value. Shifting it by 4 is equivalent to multiplying it by 16 because that's how binary arithmetic works. And then when we subtract the value of x again, the end result is x times 15. So you're often going to, like in the program, you're often going to see slightly complicated operations that look kind of like this, and you're going to scratch your head because no programmer would ever, write something as complicated as this to compute something very simple. But perhaps the programmer actually wrote the simple version, but the compiler made it a little bit more complicated because it was able to compute it more efficiently. And this version here is faster because multiplying two values on a modern CPU takes like a bunch of CPU cycles, but simply shifting it by 4 is like instantaneous. You can do it in like a single clock cycle. All right, and then probably the most important thing that you have to be aware of is that the variables that you're going to see on the stack of a program do not necessarily correspond to the variables in the C code. So you can have a C function that has 5 variables, but maybe only 2 of those variables are used at a time. Like maybe the program first uses the first 2 variables, and then after this, it only uses the other 2 variables. So the compiler will notice this, and to save stack space and to reduce the amount of memory that the program needs, it's going to combine these two variables and keep them in the same place in memory. And this is okay because after the code uses the first two variables, their values will not be needed again. So those places in memory can be overwritten with the values of the other two variables. So usually what you're going to get, if you're doing decompilation, where you take the binary code of a program and you kind of convert it back to C code manually, you're going to end up with C code that is slightly different from the original C code that the programmer wrote, but it's going to have the same end result if your decompilation is correct. So there can be multiple forms of the code. All of them are correct, but some of them are maybe easier to understand when you read them than others. So as you do this more and more, you're going to get better at converting the more complicated structures that the compiler outputted into more readable, more human-readable code that looks closer to C code that you might be familiar with. Oh, and then finally, sometimes in the CPU there are a lot of weird effects and dependencies that happen between different instructions. So sometimes changing the order of two instructions will make the program run faster because the CPU units that perform the calculations can run in parallel. So for example, I mean, obviously this can be done only if the instructions that you are changing the order of don't depend on each other. Like if you need the first instruction to calculate something and then use it in the second instruction, there's no way around it. You have to do the first instruction first. But if you're computing two things that are not dependent on each other, then you can do that in any order you want. So the compiler, in that case, will choose the order that results in the fastest operation of the program. So here you have two assembly sequences that are equivalent, but one of them will be slightly faster. So here we're loading a value from memory into EX and then adding 1 to it. And then underneath that, we load a value from EDI into EDX and then add 1 to it as well. So these loads, the memory loads, are usually pretty slow on the CPU because it has to talk to the RAM to get the right value, and this takes a bunch of clock cycles. So the CPU will work faster if you do the two loads together first, and then after that you do the two additions. And these two sequences are, they compute the exact same results. So again, when you see this in a binary program, it doesn't mean that the programmer wrote the memory references in that order. Maybe the compiler put them in that order because they're faster. So the main tool for reverse engineering binary programs is the disassembler called IDA Pro. This disassembler has been in existence for almost 20 years now. It is very full-featured and has a very long history of development. You can download the free version, which is somewhat limited in what it can do, but it's perfectly adequate for all of your needs in this class. It used to have almost no official documentation, but now there is a very good book about this disassembler called the IDA Pro book. Very, very imaginative title. I highly recommend you buy this book if you want to do anything more serious with using the disassembler. It is the best documentation that is available about it. But who needs documentation? We're just going to jump into it, and we'll see what it looks like. And I will open a simple executable that I built earlier today, and I will show you how we're going to figure out what the executable does without having source code. the more eyes on the progress bar, the faster it goes. So thank you all. Okay, I hope everyone can see there in the back row. And it looks like we're still recording. Okay, so this is a Windows VM, and I have IDA installed in it. IDA actually has OS X and Linux versions as well, but I'm going to use the Windows one. So I build a simple executable here. It's a very, very small one, 6 kilobytes. It doesn't really do much. It's built with Visual C 2008. So to open it with IDA, I will drag it into IDA. This will start the program. So there's an option that I'm going to disable temporarily. So this is what the IDA main window looks like. It looks a little bit better if you have a bigger screen than this, but this is still enough for a demo. So we have a few different views. We have the IDA view that shows you the disassembled program code. So here we have a call instruction, then we have a jump instruction, and then the jump instruction goes down there to this block, and then it continues executing through here. Then here we have a loop. So this instruction gets executed. This is a conditional. So we have a JZ instruction that's a conditional instruction, and it goes either down here or down here. So you can kind of follow the code. You also have a few different windows. The one that is interesting to us right now is the imports view. So this shows you all the functions that this program imports from the Windows DLLs. And usually you can look through the imports and kind of see what the program does. So most of these imports are just kind of standard. You're going to see them in every program. But the more interesting ones are sprintf, string length. So these two imports mean that the program does some kind of C string manipulation. And then also we see a bunch of imports from the WS232 library, which is the WinSock library that contains all the networking code. So we import the functions socket, bind, listen, accept, receive, send. So just from this window, you can tell that the program listens on a network port, accepts connections, and then sends and receives data. So on the side here, you have a list of all the functions that IDA has identified in this program. And most of these functions don't have specific names. They're just named after the address in the program where the function code is found. This is because all the names are lost when the program is compiled into an executable. But we can guess that the code we're interested in is going to be the code that calls the networking functions. So let's go to the listen function. I'm going to double click on it. And actually I'll close this to make it a little bit bigger. Okay, so this is the listen function. It is imported from one of the Windows libraries. if I press Control X, this will give me a list of cross-references to this function. So it'll give me all the locations where the program uses this particular function. There's only one such location, and that is here. So here we have a function called listen that jumps to this import. So we're going to press Control X here as well to see who calls it, and we see that we have one call from this particular subroutine. So we're going to go there, and it highlights the call to listen. So now we know that this function is the one that performs the networking stuff. So let's call it interesting func. So you just saw something very important. In IDA, you can rename any of the pieces of the program that it shows you. You can rename the function names, you can rename variable names, you can also create comments. So you can interactively add more information to the disassembly to make it more clear what the disassembly does, what the program does. So as your understanding of the program increases, you can add this understanding into IDA, and IDA will make the rest of the disassembly easier to understand as well. So now that we've renamed the function, I'm going to press Control X again to see the cross references, and I see that it's being called here, and it's actually being called from a function called start. This function is called start because that is the entry point of the executable. So IDA knew that that was the entry point and named it start, and then we named interesting func ourselves. So now IDA reflects this in the disassembly. So if you're somewhere else in the program and you're just reading some code, you're going to see a call to interesting func, and this will tell you, oh, I have seen this function again. I know what it does. I gave it this name. So it'll make it easier to understand why it's being called. So the interesting func is most likely the main function of the executable, because we have the start function that calls this one, and this one does all the work. So the start function is most likely one of the internal routines that the C compiler adds. So the start function, we're not going to look at it in more detail, but the start function sets up the heap and performs some other initialization steps that are necessary for the program to run, but they're not explicitly put there by the programmer. However, after all the initialization is done, it calls the main function of the program, which in Windows programs it calls is named winmain. So we're going to rename interesting func to winmain because we've identified what it is. So yes.
There's a start procedure at the header of every program.
Yeah.
And it ends by calling. Why wouldn't it just name what it calls either winmain or main?
Well, IDA is not that smart. I mean, IDA does name some functions based on.
Is that an unreasonable assumption on our part?
Yes, but also the start function is so IDA can name the start function because the entry point of the executable is always it's always recorded in the executable file. So IDA always knows where the executable starts, just like Windows knows where the executable starts when you launch it. But the start function, its implementation, depends on the compiler. So in the Visual C compiler, the start function has one form, and then it calls winmain. But in some other compiler, maybe there is no start function, or maybe the start function calls something else, and then that other function calls winmain. So it's not always the same. Okay, so now we know where the win main function is. So great. So we can start reading the win main function, and we can try to figure out what it does. Close this. Okay. So usually what I do is when I start looking at a function, I look at just the functions that it calls. Like, I don't really read every single instruction. I just try to get a more high-level understanding of what happens in it, like what APIs it calls, because often based on that you can guess what the goal of the function is. So all the function calls are highlighted in blue, and then here we see a call to WSA startup. It is followed by a call to socket. Then that is followed by some call to memset, and so on. So there's two main points here. One, how did IDA know to name this function WSA startup? The answer is that's one of the functions that are imported from the WinSock library, and they're imported by name. So the name is hard-coded in the executable. The same is true for the socket function. If we have a call to a function that is not imported and IDA couldn't guess what it is, then it's not going to have an understandable name. But here we're lucky because most of the functions called by this program are simple public APIs, Windows APIs. So we know what they do just by looking at their name. And then IDA has a few more smarts that help us. So for example, IDA knows that the parameters to the socket function are AF, type, and protocol. And you can find out. Oh, I don't have that. If you Google the socket function and look up its reference, you're going to see that these are its 3 arguments, and you can read the documentation on the socket function to understand what the arguments mean and what they're for. IDA just knows that their names are protocol, type, and AF. Another important thing, when you call a function, its arguments are pushed onto the stack with a push instruction. So here we have push 2, push 1, push 0, push EDI. We have 4 pushes. So IDA knows that this push is the AF argument, this push is the type argument, this one is a protocol argument. Now the first push, the push EDI, this one is not actually an argument to the function because the function only has 3 arguments. So the 4th push is actually put there by the compiler to save the value of this register so that later it can be restored. So EDI is one of the registers that must be saved before you modify it, and then the function has to restore it when it returns. So the compiler saves it here, and then at the bottom of the function it'll restore it from the saved value. Okay, so we have a call to socket, and if you go and look up what the actual constants mean, here we're just creating a normal TCP socket. Then after this, we get the return value. The return value of functions is always returned in the EAX register, which is here. So if we read the instructions after the call to socket, we see that the return value is moved into the EDI register, and then we compare the EDI register with FFFFFFFF, which is actually -1 in binary. So you can, yeah. Okay. So we compare the return value of socket to -1. This is simple error checking because socket returns -1 if it failed to create the socket. And then we have jump not 0 instruction. This instruction does a jump if the 2 values we compared are not equal. So if socket did not return -1, then we take the green branch and we continue here. Otherwise, we take the red branch over there. So now we know that this location where we jump to is the place where we go when the socket function succeeds, since it returned a value that's not -1. So we can rename that location. So I'm going to press the N key, which renames. And we're going to give it a more understandable name, which is socket OK. And you can see now that IDA changed that name in the place where it's referenced and also the place where it's the location that it specifies. So we keep reading. We see a little bit more, a few more calls. Here we have a H2NS. That's another standard API function. It converts. It's usually used to convert port numbers. So its argument, which is here host short, is most likely a port number, and it's 7B6. If I right-click it, I'll have the option to convert it to decimal. So it's 1974. So there, we have port 1974. And then after this, the program calls the bind function. So it binds to port 1974. We continue reading. Like all of these jumps here are for error checking. So if any errors happen, we follow these branches. But we're not interested in errors. We want to find out what happens when the program succeeds. So after we bind to this port, we listen on the socket. So now the program starts listening for connections. And then whenever a connection happens, we call the program calls the accept function. The accept function establishes the TCP connection and returns a socket that we can read from and write to. And we use this socket to communicate with the remote end of the connection. So there's some client, network client, that connected to us on this port, and it's going to start sending and receiving data. And we use the socket that accept returns to read that data and to write to the client. So it is important to keep track of that socket, because the value that accept gives us is the socket that has to be passed to any functions that are gonna read and write data from it. Now in this program, it's a very simple program. There's only one socket. But in a more realistic program, it's probably going to open multiple connections. It might listen to multiple ports. So you have to kind of track which socket is connected to what port. So the return value of accept is the socket, and that goes in EAX. So we move it into ESI. So now I'm going to add a comment. And you add the comment with the semicolon command. Comment. So the comment is going to say ESI equals socket, or connected socket. And you see that the comment appears in the disassembly. So this makes it easier for us to read through it and see what the meaning of these instructions is. Then we have a test instruction. Test checks whether its argument is 0. So we check if the ESI, which is the socket, if it's 0, which indicates a failure. And if it's not 0, we go here. So we're going to rename this location connection accepted. And then we have 3 function calls. Here's the first one, second one, third one. And if you look at ESI, which contains the socket, you see that ESI is being pushed as an argument to each one of these three functions. So the program calls three functions with the socket as an argument. And then after this, it calls close socket, which anybody wants to guess what that does? Closes the socket. And then after the socket is closed, the program continues, and you can see this big blue, the big blue line that shows where the program goes after this, and it goes back to this block here, where we came from. So this blue line is actually a loop. So we have a loop that executes this block and then this block. And in the loop, we call accept, followed by these three functions that we haven't figured out yet, and then we close the socket. So we're going to rename this to connection loop. So now you know that the program goes in a loop, accepts connections, and then it handles each connection through these three functions. And then it finally closes the socket. So this is a very standard behavior for a network server. We listen on a port, we accept connections, we handle them, and we repeat until the program terminates. So let's figure out what these functions do. We're going to look at the first one. We're going to name it first function, since we don't know exactly what it does, but we know that it's the first one. So we're going to incrementally, we're going to change its name based on, as we uncover more and more information about it. So for now, all we know is that it's the first one it's called. It receives one argument here, it's pushed, push ESI. ESI is the connected socket. So it's one argument, it's one function with one, it's a function with one argument, the socket. So I'm going to click on it, and that will open the function. Now this function is just a single block. There's no conditionals, there's no loops, just a single straight through block. So let's read the code and figure out what's going on. Does anyone have any idea what this function does based on the code there? That sounds about right. We have two functions called by this function. One is strlen, and then we call send. So let's look at a send first. So we want to identify what arguments are pushed to it. So the first argument to send is s. S is a local variable of this function. And IDA very helpfully identified that the s argument is actually the first argument of this function. It even figured out its type, which is pretty cool. It figured out the type because IDA knows that the send function accepts an argument. The first argument of the send function is supposed to be of type socket, and then IDA propagated the knowledge about this type up. So that's how it figured out that the argument to our first func is of type socket. So we didn't really have to do that much reversing. IDA actually did quite a bit by using its built-in knowledge. But in a more realistic scenario, you're only going to have a few of those functions that IDA recognizes. Most of the other functions you're going to have to figure out yourself. So the send function takes a socket. This is the socket that we just accepted a connection on. And then it takes a buffer and it takes a length. And the send function simply sends the contents of that buffer to the socket. Let's see where the buffer comes from. The buffer is pushed here. The ESI is the ESI register. So we need to look at where do we assign to the ESI register. So if we, and I'm sure you've noticed, but whenever you click on a register or or a function or anything else, IDA very helpfully highlights all the places where that register is used. So we have the ESI register being pushed here, and then if we look, if we go up, we see that it's pushed again as an argument to strlen, and then here we have the assignment into ESI. So we move into ESI, we move the offset of a variable called str, and this variable is a global variable in the program. It's actually not a variable; it's a constant because we never assign to it. It's in the data segment of the program, and its contents are a string called "Welcome to Snow," followed by %n, %r new line characters. And again, it looks like this because IDA was able to recognize that this looks like a string. It's like a null-terminated C string, so it very helpfully converted it into string form. If IDA couldn't, if it was not a string, if it was just like some kind of buffer of bytes, then IDA would have just shown you like a bunch of hex bytes, and then you would have had to figure out what the meaning of these hex bytes is. But since it's a string, IDA figures it out. So we have the address of this string moved into the ESI register. And then it's passed as an argument to strlen, and then it's passed as an argument to send. If you look at the third argument to send, which is the EAX register, this is supposed to be the length of the data that we're sending to the other end on the network connection. The length is EAX, which is the return value of the strlen function. So now the meaning, the intended the operation of this function becomes more clear. We take this string constant, which says "Welcome to Snow." We calculate its length with strlen, and then we give it to the send command, to the send function, to send the contents of that string to the other party of the on the network.
What is ECX?
Oh, here. It's a little implementation detail. Strlen is a C function, so its calling convention is the C decal calling convention. You can read up on it. The C decal calling convention says that the caller pushes the arguments to the function, then calls the function, and then clears the arguments off the stack. So the caller is this function. It pushes ESI, which is the argument of strlen. And then when the strlen returns, the argument to strlen is still on the stack because strlen doesn't remove it from the stack. So this function has to remove it. And to remove something from the stack, you use the pop instruction, which just like pops it from the stack. And we pop it into ECX because like we don't really care what its value is because the value is irrelevant. We just want to pop something from the stack. So we just pop it into the ECX register. The ECX register is not used for anything else, so we just use it as like scratch space.
Okay.
So that's why we pop the ECX. So one thing that I usually do when I do this kind of reversing is I open up Notepad and I kind of type notes and I try to convert this function, the assembly instructions to C code, just because I find it easier to read. So if we wanted to take a guess at what the C code of this function would look like, it would be something like this. So it would be something like this. We have this message. It's a string constant. We get its length with strlen, and then we call send, and we pass the length to send. So that's about it. Very simple function.
How do you know it returns an int?
Ida just guessed that it returns an int.
Oh, wait, oh, at the top there?
Yeah, here.
Wouldn't it be return the value of send here? If you just return implicitly?
Yeah, so notice that, so when send returns, its return value is an EAX. And then when our function returns, the value of EAX is still that return value. So this is equivalent to just returning the value that send returned. However, it is also possible that this function doesn't really return a value. Like maybe it was a void function, and then the value of send, the return value of send, is just discarded. We can't really tell from the assembly code. We have to look at whoever calls this function, and we'll have to see whether they check the return value. If nobody checks the return value, then most likely the function is a void function. Okay. So what should we name this function? I mean, now we kind of understand what it does. So tell me, what do we name it that reflects its meaning? Welcome func. So it's a good name. So now when we I just pressed escape, which moves you back one level. So this is the win main function. So we have a call to welcome func, and we know what it does. It sends a welcome message. Maybe we can call it send welcome message to be like even more explicit. So now let's move on to the second function. Now the second function has so the second function here has two parameters. First one is still ESI, which is our connected socket. The second parameter, however, is EAX, which is calculated using the LEA instruction. LEA stands for Load Effective Address. It's not really important what it stands for. It's important what it does. LEA calculates the address of a variable. So in C speak, it would be equivalent to the ampersand operator. So here we have a local variable called var124, and then the LEA instruction. The LEA instruction takes the address of var124 and puts it in EAX, and then we push this as an argument to second func. So if we wanted to put a comment after second func to make it clear what happens, it would be called kind of like this: s and then var124. So we have a call to second func with these two arguments. What is var124? We don't know. It's just a local variable in the stack. We have no idea what its name is or what its type is. Yes?
What is with the EP plus?
Okay. So when you enter a function, the function sets up its stack frame, which is it reserves some space on the stack for all of its local variables, and then it uses the EBP register to point to that stack frame. EBP stands for base pointer, so it points to the area of the stack that is used for local variables. And because you have multiple local variables in the same function, it addresses each one. It refers to each one by adding a value to EBP. So EBP kind of points to the beginning of that area, and then depending on what offset you add to it, you're referring to different functions. To different variables. So that's you're going to see the EBP addressing pretty often in most C code. Okay, so let's go into second func and try to figure out what it does. So IDA, the second function is of type socket, but it doesn't know what the type of the second argument is, so it just says integer. But that's most likely wrong. IDA just doesn't know. But we can correct this once we figure out what the type is. So let's look at the code. The code is a little bit more complicated, but again, if we focus on the functions that are being called, we see that first we call the receive function, which reads from the network, and then the arguments to receive are s, which is the socket, then a buff argument, that's the buffer that we read into. So we read from the network and store it into this buffer. And then this buffer is, this argument is the address of a local variable called buff. And then again, IDA was smart. It knows that this variable is being passed to receive as the second argument, so that's why it called it buff. If it didn't know what its name should be, it would have called it var underscore some number. Okay, so we have buff, which is a buffer on the stack. And then we have len, which is how many bytes we're reading from the network. We're reading 1 byte. So this receive function reads 1 byte from the network into buff. And buff is a character buffer. So we read 1 byte from the network. What happens after that? We do some other stuff, and then I'm going to skip through a few of the less important pieces. But then we have a loop here. So the loop is identified by like this big dark blue line. So we have a loop. So the remaining function is the loop. So it reads 1 byte and then it goes into a loop. In the loop, it reads from the buff variable and it puts it into the AL register. The AL register is a single byte register. So this basically takes the byte that we just read and puts it into AL. AL equals byte just read from the network. And then we compare this byte with the number D. The number D is actually the new line character. Is it? It's either new line or line feed. I think it's new line. Line feed? Okay. So then the comment for this would be, is the byte equal to line feed? And then this conditional jump here jumps if they're equal. So byte is Whoa. I think it didn't like the name being starting with byte. Okay, so if the byte is a line feed, we like jump somewhere down there. But if it's not a line feed, then we do another comparison and we check if it's a new line. So we go here, is the byte equal to a new line? And if it is, the JZ command jumps here. Byte is new line. Okay, so what happens if the byte is a new line? We go to this block. And this block is the end of the function. We return. So it seems like this function reads from the network, and then if it reads a new line character, it returns. So most likely this is a loop that keeps reading bytes from the network until it reaches a new line. Again, this is a very common thing for a network server to do. You're just reading some command, and then when you hit the new line, that's the end. So what happens if it's not a new line, if it's just a regular character, let's say A? We take the character, which was the byte, which was in the AL register, and we move it into the memory at address ESI plus EDI. So here we're computing the address and storing the byte at that address. So what are ESI and EDI? Let's look at where they're assigned. So the assignment to ESI starts here, where we XOR ESI with ESI. What happens when you XOR this? When you XOR two numbers that are the same? Sorry? Yes. So when you XOR two bytes, they're the same. You get result 0. So the XOR ESI instruction is actually equivalent to ESI equals 0. It's an assignment. Why does the compiler do XOR ESI instead of doing a move instruction to assign a 0? It's faster, and it's also smaller because the XOR instruction is I think 1 or 2 bytes, but then the move would be longer. So it's a little optimization. So ESI starts as 0, and then it's being used here for our address, and then immediately it gets incremented. So ESI is actually a counter in the loop, because on each iteration of the loop we increment it by 1. So we can actually rename ESI to counter. So that's kind of crazy. IDA lets you rename registers. I don't use it very often, but in this case, it makes the code a little bit simpler. Yeah.
I think that only works on the new version. On the old versions, you have to highlight from the register to the
Oh.
Like if they use the freeware version,
Oh, it doesn't?
you have to highlight from ESI to another ESI and then hit.
Okay. Well, you don't really have to rename registers very often. You can always just put a comment that explains what the register is. So here we increment the counter. So the equivalent in C would be counter plus plus. And then here we are storing at an address that's EDI plus counter. So EDI is probably a buffer, and then counter would be an array index into that buffer. This is like a very common pattern. So in C, it's probably equivalent to something like EDI counter equals AL, where EDI is just a array of bytes. So let's look at where EDI comes from. So we have EDI highlighted. we go up a little bit, and we see that EDI is assigned arg4. Arg4 is actually the second argument to the function. This is how IDA names arguments. So let's rename this argument to a buffer argument. Buff arg. And as I renamed it, IDA immediately updated the prototype of the function up here. So now the function takes buff arg. And then I'm going to put a comment here that says EDI equals buff arg. Okay, so now we know that the function takes a socket and a buffer, and then EDI refers to that buffer. And then inside the loop, we are reading bytes, storing them into that buffer, and incrementing a counter. So it turned out that the code of this function, the operation of this function is actually pretty simple. It just reads bytes and stores them in a buffer. And then after we store the byte into the buffer, we go to this block down here where we call receive again. So it is truly a loop that keeps iterating, reading bytes into a buffer until we hit a new line character. So there's another cool thing that you can do in IDA here. I think it's edit. It's the Y key. I don't know what the command is in the menu. The Y key lets you change the prototype, which allows you to set the types of the arguments. So we now know that that the second argument is not an integer. The second argument is a pointer to a character buffer. So we're going to change its type, and now everything looks nice. So we kind of figured out what this function does, right? So in summary, you call the function, you pass it a buffer, and it just reads from the socket into that buffer until it hits new line. There is a security bug in this function. Can anyone tell me what the security bug is?
Right past the side of the buffer.
Yes. So this function, the loop in this function, it keeps going until it receives a new line from the network. But what if we keep sending A's and no new line? Like we can send 100 megabyte of A's, no new line. The code will just keep iterating through the loop and increment the counter every time right into the buffer. So it'll fill the buffer and then it will continue writing past the end of the buffer. This is what's known as a buffer overflow, and they're pretty common and pretty cool because it turns out you can exploit them to actually take full control of the application. I think there's going to be some more. There's going to be other sessions that are going to talk about the exploitation in more detail. So let's see what this buffer is that we're writing into. I'm going to go to the place where second func is called. Oh, before that, what should we call this function? Huh? Okay, we're going to call it read from socket into buffer. So this is the place where it's called. And you see that because we changed the name of that argument inside the function, IDA propagated that name. So in the caller, now we have buff arg listed here. And then the var1234 variable, IDA automatically renamed to buffarg. So it's very smart. Like the propagation of names and types is pretty cool. So this is the buffer that is being passed to that function. So where is that buffer? Well, the buffer is a local variable inside the winMain function, and we know this because in the winMain function we get the address of this variable, and we refer to it by offsetting from EBP. And since EBP is the base pointer that points to the local stack frame, this means that the buffer is on the local stack frame. So with our newfound knowledge, we figured out a security bug in this program. So the program listens on a port, accepts the connection, sends a welcome message, and then just reads from the network whatever you send it. So if you send it a message that's too long, longer than the buffer, it will override the buffer and corrupt memory past the end of the buffer. So the one remaining thing is to figure out how long this buffer is. So here's how to do this. We're going to go to the beginning of the function at the top. This is where IDA lists all the local variables that it has identified. So here's the local variables. So it lists the names, their types, if it knows what they are, and then also the offset from EBP. So EBP is the base pointer. The buffarg variable, it starts at EBP minus 124. You can see that the next variable that IDA found starts at offset EBP minus 24. So this means that the difference in the addresses of the two variables is what? You're an instructor. You can't answer these questions. You'll get a chance to impress them when you're up here.
You should show them the stack view.
Huh?
You should show them the stack view.
Oh.
Because you can hit the numpad star. Go in the rank.
Too complicated. Okay, well, I'll do this and then I'll show you the stack view. So by subtracting these two numbers, we see that the difference between buffarg and the next variable in the stack is 100, but that's a hex number. So 100 in hex is 256. So we have a 256 byte buffer in winMain, and then we're reading into it an unlimited amount of bytes. So that's the buffer overflow. Now the stack view that Aaron mentioned, you can get there if you double-click on any of these variables, and it opens a new window here. It's called Stack of winMain, and this view shows you exactly what the stack would look like at runtime. So when you call a function, you push its arguments on the stack, and then you do the call instruction, which pushes the return address, and then jumps to that function. So this is how the function knows where to return. The return address is pushed onto the stack together with the arguments. And on the bottom here, we see the arguments. So these are the arguments to winMain. If you've done any Windows programming in C, you'll actually recognize these variable names. These are the standard argument names of the winMain function. Then we have this thing R, which is the return address. That's what IDA calls it. Then we have this thing S. It's used to save the old frame pointer. You don't have to be concerned with it. And then after this, we start with various variables that are referenced inside the function body. So we have the adder len variable, we have the adder variable, we have DST. We have two other variables that IDA could not could not identify, we can go and manually, see where they're referenced and try to understand the code. But for our purposes, that's irrelevant because our goal was to understand not all of the program, but enough of its code to be able to do something interesting with it. And now that we know where the buffer overflow is, we can trigger it. We can write a network client program that connects to this port, sends the data, triggers the buffer overflow. We don't need to know all the details of every single function. So let's scroll up to where buffarg is. So here's buffarg, and you see that IDA shows it like up here, and then DD means that it's a double word, and then after that it's followed by DBs, which are bytes. So IDA has all of these bytes on the stack frame, and it doesn't know what they are because there's no references directly to them. That's why they don't have any names. Now, the reason there's no references to them is because all the uses of buffarg happen through its through its base address. So the program takes the address of buffarg and never refers to the individual bytes inside it. But buffarg is an array of a bunch of bytes. So that's why you have all of these unidentified bytes here. They're simply part of the buffer. But because IDA doesn't know that this is a 256 byte buffer, it doesn't fold up the bytes into it. So if we scroll down, there's going to be 256 of these bytes, and then we're going to have the next variable, which is here. It's called adder. So this is how we know that buff adder is actually a 256 byte array, because we can count these bytes and we'll see that there's 256 of them. Now, it is theoretically possible that buff adder is actually not a character array. Maybe it's a structure that contains a character array of 256 bytes followed by this adder field. There is no way for us to know because we don't have any type information. We just have to guess the types. So the programmer might have put these two things into a structure, or they might have been two separate variables. In the assembly code, it's going to look exactly the same. So because of that, we have to guess what would make more sense. And you do this based on experience. You do this based on having seen a bunch of C code, knowing what code usually looks like and how you would write it. So if you had to write a program that implemented a network server and read from the network into a buffer, you would probably put the buffer as just a normal variable in the stack. You're not going to put it in some kind of more complicated structure. So we're going to guess that this is what the programmer did, but there is no way to know for sure. So the types that you identify might not match exactly what was in the original C code, but the behavior of the program is going to match because the behavior implemented in the assembly is exactly what gets executed. So I've talked for quite a while. Hopefully this will give you enough information to start, and you can take some program, like a very simple program, load it up into IDA, and you can try to sort of repeat these steps, see what the program does. I think we can put this program on the website, so you can actually download this very same executable and just kind of repeat these steps as an exercise. And those skills are going to be pretty useful later when you try to exploit some programs, and when you try to figure out what the internal layout of a program is. So I think that's all I had for today. If you have any questions, let me know now. You can also always email me at my email address that was on the first slide. I think we'll put it on the website as well.